All right, so we described the process of solvating ionic solutes by polar solvents. Okay, so the next category that I want to deal with are the category of dissolving polar solutes by polar solvents. And this is also a solvation process. Okay? It's a solvation process. All right. So one of the most common polar substances that we dissolve is sugar. I mean, how many of you put sugar in your tea? You're doing solvation. Okay? The sugar's been solvated. Okay? So let's look at it. Now, table sugar is a complex sugar. It has two ring structures. That's a little bit more complex than I want to be. Let's do something that has only one ring structure. Okay? So if I'm not mistaken, glucose has an oxygen in a six-sided ring. Well, I didn't quite draw that very well. Let's do it down here. Okay? It's a side there. Okay? And then there are these oxygen-hydrogen groups sticking off all over the place. And there's one where you've got an extra carbon sitting up there. Okay?
What makes it taste sweet, though?
What now?
What makes it taste sweet?
It's the way that these polar locations and the shape of it interact chemically with the sensors on your tongue. Can you make sugar?
Yeah.
No, only plants can make sugar. Now you can use plants to make sugar, but you personally can't make it. That's true. I don't know of a way to do it. There may be some way to do it in a lab that I'm not familiar with. Okay, but this is a real simple sugar, and if I'm not mistaken, this is actually a reasonable representation of glucose. Okay. All right. So remember that when we were looking at particle interactions in the last unit, we said that if we have an alcohol and we put it in water, that this end of the alcohol is very polar and will do what's called hydrogen bonding because of that OH. And it will dissolve in the water. And this side over here, while it doesn't want to be dissolved in the water because it's nonpolar, it's sort of drawn into the water by this. Remember talking about that in the last unit? How we dissolve things that have polar ends on them and nonpolar ends on them? Well, look at all the polar ends on this stuff. Okay? All these O's and H's can be attracted to water molecules. Now remember our water molecule structure. We've got a large oxygen that's partially negative and a couple of smaller hydrogens that are partially positive. Okay? And in fact, there are really two spots on here where the lone pairs are located where it's partially negative. All right. Each one of these OH groups can hydrogen bond 3 times to a water molecule, or 3 different water molecules. So I can, this end of the hydrogen OH group, this hydrogen end of this OH group is partially positive. And so it's attracted to the partially negative end of water. And so there's a hydrogen bond there. Okay? This oxygen, because of those 2 lone pairs, going back to units 2 and 3, can actually hydrogen bond to 2 different water molecules, to the hydrogen end of 2 different water molecules. Okay? So I can hydrogen bond twice. Okay? And that happens in all these places. That's true. Yes. That is true. I didn't break off the hydrogen here, so I'm trying to figure out how to do this one. So we got all these hydrogen bonds going on here. And it's starting to get kind of busy, you know. We're having a hard time drawing all this kind of stuff. Wait a minute, that goes to the hydrogen end here. All right, because there's so many places for this to happen. Now this oxygen here also has a couple of lone pairs. It's not quite as polar. So it doesn't do hydrogen bonding, but it has a polar attraction to water in two places. So this oxygen is attracted to two waters. Now, they're not stuck really, really hard. It's kind of like Velcro. They stick and they unstick. They stick and they unstick. Okay? But there's an attraction there. It's not hydrogen bonding, but it's an attraction. Lots of places for water to grab a hold of that sugar molecule. Now, sugar, in at least the kind of sugar you have at home, and even this, if you buy pure glucose, comes in a crystal form. Okay? When there's no water around, those hydrogen bonds work to link it all together into a crystal. Once you put it in water, the water molecules start to kind of pull on those hydrogen bonding locations, kind of like their handles. You can kind of think about that pulling action as pallbearers holding on a, I know it's kind of a sad thing to think about, but on holding up a casket. Okay, there's places to hold on to it, just like these water molecules can hold on to these places on the sugar molecule. Okay, and carry it along. And so it allows the sugar molecule to be carried along into the matrix of water, all those water molecules. Okay? That is a form of solvation when you have a polar substance being dissolved in a polar solute. It might be some other polar solute, but that's the method or methodology, the theory, the model really. Well, I guess it is a theory because it's well accepted for taking solids that are polar, like sugar or an alcohol, and dissolve them in water. They get pulled along by those hydrogen bonds and polar attractions. Does that make sense? Any questions? Now remember, ask yourself, Mr. Taylor gives me a quiz in which I have to write an essay and describe this solvation process, can I do it? If you can't, you need to ask more questions like you were doing a while ago. Those are really good questions. The difference is that it's specific locations. Remember when we had an ionic substance like sodium, the negative end of water can join up anywhere. There's no specificity to that. It just makes a skin around it. Okay? So any ion, any kind of ionic substance, the water just makes this shell or skin all the way around it. Okay? Whereas these are joining up at a specific location and doing what's called hydrogen bonding, which is somewhere between a strong polar oppositely charged type of attraction and actually sharing electrons. Okay? Just a different kind of process, very, very specific in the location. All right? Everybody got that? Nobody has any questions. Everybody's so sure that they can do a quiz on this and answer this as an essay. I don't know. You got to be, what you want is prepare yourself for that. Nobody has any questions? Yeah.
Okay, can you
Hold on, Darrell first, then you, okay?
So on the hydrogen, you can only get one oxygen on each one.
Yeah, that's not that critical that you understand that, but you're right. Hydrogens can only hydrogen bond once. The oxygen can hydrogen bond twice because it's got two lone pairs. If we go back to the structure where we drew out the structure of the structure of a water molecule, and remember the modified electron pair shape. This is the modified electron pair. Well, actually, yeah. And then I had a set of electrons up here and another set of electrons up there. Okay, does that make sense? Remember that? Well, both of these places where the lone pairs are located, they can both do hydrogen bonding at that location. So that's why you can do it twice on oxygen, but only once on a hydrogen. Okay? So this OH group is just like water, only instead of being a hydrogen on this end, it's a carbon over there. Okay? All right, Evelyn?
I don't know, I forgot what else.
Huh?
Oh yeah, just like, can you summarize what like you lose me with all your drawings. Like, can you just summarize what you just did right now?
Yeah, what I did was a summary. Okay. I mean, you can get a lot more complex in this. Okay? Dissolving polar solutes by polar solvents is the result of these permanent dipoles and the attraction between them. Okay? So water has, because of the arrangement of water, where this is more electronegative than this is more, there's going to be places for hydrogen bonding or just polar attractions to occur. Anything that has a permanent dipole, where I got permanently negative and permanently positive sides, that's a permanent dipole. And there's an attraction between them, between this one and the next one. So if I got another one that's kind of like that, this positive end is attracted to the next negative side. Okay? Because of the opposite charges. That's a polar attraction. There's an attraction between this particle and this particle. And so, in order to get something that is polar in a crystal or in a solid to separate and join up with a solution, it's all about getting those opposite charges, where they're completely full opposite charges like an ion, or partial opposite charges like in a polar location. It's all about getting enough of that attraction involved that it'll let go of the actual bond that occurs. Okay? That makes sense? Or not bond, but I mean, you replace one kind of attraction with another kind of attraction to get all of those separate out and join up with the water. Become one single particle in a bunch of water particles. Okay? That's the solvation process. Is that enough of a summary for you?
Yes.
Okay. But now, what you have to do is fill in the blanks in some of that. Be a little more detailed like that if you're writing an essay. So all these details are kind of important. You don't have to write every detail I've mentioned, but you have to have enough that actually explains the story. How did all the little Timmies in the neighborhood cut down that cherry tree? I don't know. Something. Okay? How did that happen? Fill in the details. In other words, you're not telling the story if you just say a bunch of little boys in the neighborhood cut down a cherry tree. That's not telling the story. That's kind of boring, isn't it? Okay? What you have to do is fill in all the blanks. It's an interesting story. You have to tell the story. Okay? Any questions about that? All right. So that's dissolving polar solutes by polar solvents. So the next thing we want to talk about is nonpolar solutes and nonpolar solvents.